Hey everyone, welcome to week 8, part A. This is the only part to week 8. There is no part B. So in week 8, we are going to cover two topics. We are going to talk about recursion, and we are going to talk about object-oriented programming. Alright, so let's first talk about recursion. So you've actually have seen recursion already. If you remember that lab assignment when we were working with lists, and it was the one with the list that had 5 elements in it that had information about sales data, and at one point you asked the user, hey, is this information correct? When we put that inside of a function called check sales. Inside of that function definition, after we asked the user, hey, is this correct? And then if they said no, we let them update it. After the update, we then called check sales again. So that was actually an example of a recursive function. So a recursive function is a function that calls itself, which sounds kind of weird, but it's basically a function that has a function call to itself, to the same function, within its function definition. So this week we'll talk about, sort of formally what that looks like, what that means, why we have them in the first place. So let's talk about the why first. So why do we have this weird sort of setup in the first place? Why would we have functions that call themselves? Well, this is super useful if you have what we consider a recursive computation. So recursive computation is some sort of calculation or problem, and it's solved by using the solution to the exact same problem, but with smaller inputs. So it's a problem that you can break down into smaller pieces and then sort of put them together to solve the bigger piece. Alright, so here's an example. So we're going to drive this recursion discussion by working off this sort of example. So the goal with this example is we want to write a Python function that will print out triangle patterns that look like this. So, it's a right triangle, and we should be able to say, okay, what is the length of the side? The two sides have the same length. In this case, they both have length 4. And it'll show out this sort of triangle pattern shape used with these square brackets. So again, that's going to be our goal, and we're going to build up to how we're going to write this function, both in a way that is recursive, meaning in a way that there is a function call to itself to do this. We'll also show a way to do this that's not recursive. So this is what we're going to do just in terms of logistics for this example. So we'll name our function print triangle, and we'll give it one parameter variable. This parameter variable that we'll give it is side length. So again, in this example, the side length would have been given the argument 4. So we're assuming that the two sides have the same length. Alright, so here's one potential approach. This function, you'll note, does not call itself. There is no function call to print triangle within this function definition. This is just sort of a normal function. So this is an example of a function that is not recursive. That said, I do want to point out this print line right here. This has something that has been covered in the book, but we haven't explicitly talked about it yet in our videos. So this print statement right here, where I have print this string asterisk val, so you can actually use the times operator. This is the, the multiplication sort of operator. You can actually use that with strings, and what happens is you have a string, and then you can say times some integer. So string times some integer, so you are sort of mixing types here, and what that will do is it will repeat the string however many times you give it. So for example, if I say print, here, let's open up idle for an example. So if I do, print hello times 5, basically this will display the string hello 5 times in a row. It's going to repeat this string. So we call this a string repetition operator if we are using it with strings followed by an integer here. So it's pretty useful. So let's just sort of briefly talk about this really quick, how this works. So here's a function definition for print triangle. So again, if we give it a side length, say 4 in the previous example, this for loop will go through the range 1 comma side length plus 1. So it'll go through 1 comma 5, right, because we don't include that last number in our range. So val will get the values 1, 2, 3, and 4, and it'll print this sort of, not square shape, but this sort of shape that's coming out however many times val is. So the first time around, val will be 1, next time val will be 2, then 3, then 4. And again, this function is not recursive because it does not call itself. Now, let's talk about how we could write it recursively, meaning how we could write this function using recursion. So this function right here does the exact same thing as the previous function. The difference, though, is this third line of code right here, this line of code where I say print triangle parentheses side length minus 1. So that is a function called toPrintTriangle within this print triangle function definition itself. And I know this is kind of weird, but I promise I'll give you the tools to sort of get you set up to figure out what this code is going to do. So a couple things I do want to point out with this recursive approach. We do have sort of a conditional statement here. It's very common to use conditional statements when you're dealing with recursion. We'll talk about the why in a little bit. But essentially, when this code goes, it's going to keep calling itself so long as the side length is still greater than 0. Which makes sense because we don't want to print anything if, you know, there's no side. We'll talk about sort of the nitty-gritty of how this works in a bit, though. But again, takeaway from this right now, this function definition and this function definition, they're going to display the same triangle. It's just this one right here is not recursive. This one is recursive because it calls itself within the function definition. So one thing that I do want to point out about this greater than 0 check, it is pretty important. Before we actually get too far here, let's take a step back to this and let's walk through an example, and then this greater than 0 check will make sense. So let's say, for example, I have this function definition and I say print triangle 4, meaning let's print a triangle where the side length is 4. So I'm going to draw sort of an example of how you would trace this program, meaning how you would sort of outline this program on paper and how it works. So what I'm going to do is I'm going to first say, okay, here's our function. It's print triangle. That's what I'm going to write for print triangle because I don't want to have to write out the whole thing. So print triangle, let's say we're calling it with 4, right? We're going to do this example that we were sort of working with. So when we call this function, with that function call right there, first thing we do is this sort of if check. If side length is greater than 0. Well, in this case, that's true, right? The side length right now is 4, because that's this argument right here. And it's true, right? 4 is greater than 0. If the side length is greater than 0, then we're going to do these 2 lines of code. These 2 lines of code, the first one is another function call. All right, and this function call is to print triangle, and the argument is side length minus 1. All right, so side length right now is 4, which means side length minus 1 is going to be 3. Now just hang tight for now. We'll talk about what exactly that means in a second. But for now, just sort of keep writing the rest of this function call right here. So we have this if, it's checking to see if side length is greater than 0. Then we call print triangle again, and then we do this print statement, right? Then we print, you know, basically this string 4 times, right? Because right here we say print this string side length times, and right now side length is still this 4 because we are in this function call right now. We're still inside of this box right here. So that's sort of an outline of what we're going to do. Now, this is a little bit different because this outline has itself this function call right here. So the rules with these sort of trace outlines is you just sort of make an outline top down of what the function call is doing, but after you do that, if there's a function call within it, like we have right here, we have another function call to print triangle, that means we need to write another outline for that specific function call. So now we're going to do the exact same thing where we're just sort of writing an outline of what the code is going to do, except this time we're writing an outline for this function call for print triangle 3, where side length is 3. Alright, so right now we can sort of ignore this first diagram that we drew, and now we're going to do the exact same thing but for print triangle 3. So now we'll do the same sort of thing. We run through it, we check to see, hey, is side length greater than 0? It is, right? 3 is still greater than 0. In that case, you're going to do two things. You're going to print triangle, we're going to call the function again, side length minus 1, right? Side length right now is 3, so side length minus 1 is going to be 2. And then we'll do this print statement. We'll print out this thing, and we're going to print it 3 times, right? Because the number of times we're printing it is whatever side length is right now, which is still 3. Cool. So there's an outline for that one. Now looking at this outline, we see, all right, here's another function call. So guess what? We have to write an outline for that function call. So same sort of thing. Print triangle 2. And now we'll write the outline for this one. So in this case, side length is 2. And we do this check again. If 2 greater than 0, yes, it is. So that means we're going to do these 2 lines of code again. We're going to print triangle of side length minus 1, which is going to be 1. And then we'll print this. Alright, we keep going. We still have a function call here, which means we have to draw our little outline for that. Print triangle of 1. Same thing, we do this quick check. If the side length, which is 1 right now, is greater than 0, that is, right? So now we're going to do the same stuff again. If it's greater than 0, then we'll print triangle. We'll call this function again with side length minus 1. So we'll call print triangle. Side length minus 1, that's now going to be 0, right? Because side length right now is 1. And then we'll also print this out. Right now, side length is 1, so that'll just be repeated once. Now, we see another function call, which means we have to write the outline for this one, which is print triangle of 0. And this is where it starts to get a little bit interesting. So in this one, when we're looking at the function called a print triangle 0, where side length is 0, we do this if check, right? If 0 is greater than 0, but it's not, which means we're not going to do either of these 2 lines of code, and there's no other code to do, which means this is sort of the end. There's nothing there going on. Alright, so all we've done so far is we've just sort of written an outline of what we call the trace. So this is sort of the outline of what's going to happen when the code runs. So to actually sort of follow through and sort of execute by hand the running of the code, what we do now, after we've drawn the outline, we go back to the start, which was up here, right? This was the beginning. And what we're going to do is we're going to go through the start, just top down, and run the code. Now the rule is when we run this code, if we hit any function call, meaning any of these things circled in this purple color here, if we hit any of those, the rule is we have to complete the entire function call here before we finish the rest of the code. So again, we'll go top down, and I'll sort of outline what we're doing in orange just so you can follow. So we're going to start top down. We start here, and we just go top down. So we do this check. Yes, that's true. So then we do this function call. Now again, the rule is before we do this line right here, where we do this print, we have to completely finish this function call here. So that means we're going to follow this to here. And it's the same rule. We go top down, and before we can do this, we have to completely finish this function call here. So now we're going to follow this function call again. Same thing, top down. If we hit a function call, we need to do that first. So we hit a function call here, so we follow that. Cool, top down. We hit a function call, so we need to follow that. Now this is where it gets interesting. We don't do anything here, right? This PA01, or this print triangle 01, we don't actually run any code, right? We had that check if side length is greater than 0. Well, it's not, so there's no code to run. So that means we are finally done with that function call, which means we can come back to where we came from and finish the rest of this code, which means we will go ahead and print this right here, this string, one time, times 1. Cool. So now we've completely finished this one, right? So now we can go back to where we came from, which is this one over here. We've now finished this function call here, so now we can fall through and do this print, which means we're printing that. We have that 2 times. Now we've finished this completely, which means we can come back from wherever we called print triangle 2, which was this part right here. We've done this now, so now we can do this, which means we'll print this. Running out of space here, which means we can print this 3 times. Awesome! Now we've completely done this, which means we can come back to where we made that call in the first place, which was here, and now finally finish this part here, which means we will now print 4 of these and pretend there are 4 there. That looks a little bit prettier. So now at this point, we have finally finished that function call, this print triangle 4, which was the original function call in the first place. So I know this is sort of a lot, but I'll define sort of this outline practice later on. But I just wanted to give you sort of an overview of what tracing recursion by hand sort of looks like and how it works internally. Keeping that in mind, if we remove that greater than 0 check, essentially what will happen is this function call to print triangle, it will just keep happening, right? When we did this outline over here, right here with this print triangle of 0, we knew that that was the end because we have this line of code right here that says, hey, only do this stuff if the side length is greater than 0. If we don't have this check, it's going to keep running these 2 lines of code forever. So that's sort of important to note with recursion. You have to make sure that you have sort of a step that handles the smallest piece and will sort of stop the program so that we don't have this sort of infinite loop situation where it keeps running. So for recursion to work, there has to be special cases for the simplest inputs. In this case, it's the smallest inputs, right? So in this case, when the side length is 0, our function stops, right? That's sort of the special case for the simplest input. If there's no side length, you don't print anything, right? Because the whole idea is that we're printing these sort of square rectangle shapes however many times side length is to display that triangle. If the side length is 0, we don't have to print anything. So you have to make sure that you have this sort of extra case, this special case for handling the simplest inputs. So for recursion to work, there are 2 requirements. Every recursive call must simplify the task in some way. So in this previous example, we see that this function called a print triangle within the function definition, it simplifies the sort of computation approach that we have going on by subtracting 1 from the side length. So every single time you make a recursive call to the function, that argument should be different. That argument should be getting simpler. It should be getting smaller or, different, or something that makes it closer to the final solution. So every recursive call must simplify the task in some way. And then there must also be a special case to handle the simplest or the smallest task. So in our case, again, the way we simplify the task each way with each recursive call is we subtracted 1 from the side length. For the second requirement, in our previous example, the special case was we only did printing if the side length was greater than 0. So then the special case would be if the side length is 0 or less, but if the side length is 0, just nothing happens. So that would be our special case. Alright, so you might be asking at this point, why do we do recursion at all? It looks a little bit complicated. What's the point of it in the first place? Well, there's sort of 2 scenarios where you would use it. So the first scenario is probably the more likely scenario where you would use it. So sometimes it's actually easier to write code for something using a recursive function. And I'll show you an example in a second. But yeah, sometimes it actually makes more sense to use recursion. It just makes it easier to understand your code and write your code. And then there are some scenarios where even if it's not necessarily easier to code your function using recursion, your code might actually run faster if you do use recursion. Now, for this class, that's not super important, but in a real-world scenario, maybe you're writing code that saves someone's lives. I don't know. Obviously, if the code is faster, that's going to be important, even if it's just by 1 second. So there are some real-world scenarios where it is super important to be able to shave off seconds from your code runtime. But the scenario we'll sort of focus on is sometimes it actually is easier to write code using recursion. So here's an example of that. So let's talk about something called the Fibonacci sequence. So if you're not familiar with the Fibonacci sequence, that's okay. It's just a sequence of numbers. It's a math thing. It's a sequence of numbers where each value is basically the sum of the 2 previous values. So the sequence starts with 1 and 1. So those are the first 2 numbers in the sequence. And then to get the next number, you add those 2 previous numbers. So you add 1 and 1 and you get 2. To get the number after 2, you add 1 and 2 and you get 3. To get the next number, you add 2 and 3, you get 5. Next number, you add 3 and 5, you get 8, and so on. So each next number you calculate by adding the 2 previous numbers. That's the Fibonacci sequence. So let's say, for example, you wanted to write a function that would return the nth number in the sequence, right? So, for example, if you wanted the first number in the sequence, that would be number 1. If you wanted the second number in the sequence, that would also be number 1. The third number in the sequence would be number 2. The fourth number of the sequence would be number 3. The next one would be 5. The next one would be 8 and 13. So this is a function that basically tells you, at any position in the sequence, what is the number that is there. So because the Fibonacci function, well, not function, but because the Fibonacci sequence relies on two previous Fibonacci numbers to get the next one, it actually makes sense to code this recursively, because you basically use the result from the smaller two previous function calls to calculate the next result. So again, the rule is with the Fibonacci sequence, the first two numbers in the sequence are 1. So in this case, in our recursive function definition, we have this sort of simple case handling scenario where we check and see, hey, are we looking at the first two numbers? If so, just return 1, right? Because the first two numbers, you return 1. Cool. And then for all other scenarios, what you're going to do is you're going to figure out the previous number, which is this F1 here. So the previous number in the Fibonacci sequence, which is basically, the number at your current position minus 1, right? Because that's the previous position. And then you'll also figure out the other previous number. So you're going to figure out the two previous numbers in your sequence by subtracting 1 from your current position and then subtracting 2 from your current position. That's how you're going to find the two previous numbers. You just do the function call again, but you do it with the two smaller numbers. So then again, the rules with Fibonacci is you take the two smaller numbers and then you add them together. So in this case, there's two recursive calls. We have a recursive call to this Fibonacci sequence, but the one previous, and then the next one is the Fibonacci sequence, but the two previous numbers. And then you add them together, which is the rule, right? You take the two previous ones, add them together, and you return that result. So in the case of Fibonacci, to determine, the number at some position in the sequence, it actually makes a lot of sense to write your code recursively. It would be a lot more complicated to write your code not using recursion. Here's one more example of where it actually makes sense to write your code recursively. If you feel up to it, I would recommend going ahead and trying to determine what this mystery function is. And the way you would go about doing that is, maybe picking a number to be the original argument, to be the one of the arguments. So maybe try it with, 3, then try it with 4, and try to figure out what this is calculating. And come back, unpause the video when you are ready to see the answer. Alright, so this mystery function, this actually returns the factorial of the inputted argument. So the factorial is that sort of exclamation point thing that you might have seen in math class before. If you do like n exclamation point, that means you basically keep multiplying n times n minus 1 times n minus 2 times n minus 3 and so on. And as you can imagine, anything that's sort of sequence-like that relies on previous values in the sequence, if you write code for it, it's going to make sense to write code for it using recursion, because you use the previous results to build up to a bigger result. So this is another example of where writing code using recursion actually makes more sense. Alright, so in the next video we will talk more about tracing recursion by hand, so we'll do a lot more of those outline drawing examples that we did earlier. So I will see you in the next video.